Imagine the marketing team achieves a massive win. They secure a record-breaking order, revenue targets are shattered, and the company prepares to scale. But down on the factory floor, that sudden demand triggers a crisis. Machines break down without warning, defect rates spike, and the staff is forced into endless, exhausting overtime shifts just to keep the line moving. Ultimately, deadlines are missed, and the client cancels the order. This phenomenon is known as death by success, a scenario where an unmanaged back-end operational system collapses under the weight of front-end victories. Executives frequently misdiagnose this problem because they fall for the illusion of busyness. They walk onto a loud, highly active factory floor, see constant motion, and assume they are looking at a highly productive environment. But activity does not equal throughput. Those running forklifts might simply be moving defective parts to a scrap pile, and those loud machines could be running empty while waiting for materials. To understand actual capacity, we have to look at the system's constraint. The theory of constraints dictates a simple physical law. The maximum speed of your entire factory is strictly governed by its absolute slowest operational node. Upgrading any part of the production line that is not that core constraint will not increase your total yield. It is mathematically guaranteed to generate massive waste. Consider the case of Siam Master Bakery, a B2B supplier that found itself buried under a critical backlog of industrial butter croissant orders. Management's immediate reactive solution was to request 10 million baht for a brand new tunnel oven. They assumed that because baking was the final step, the oven was the reason they were too slow. This diagram maps their actual production process. The sequence is straightforward. The mixer prepares the dough, the proofing room lets the yeast rise, and the tunnel oven bakes the final product. To find the true bottleneck, we don't look at the machines themselves. We look for the physical evidence of delay, a mountain of work in process. The raw dough was accumulating entirely in front of the proofing room. Because the proofing process was so slow, the existing tunnel oven was continually starved for material, sitting empty and idling while burning expensive fuel. This exposes the danger of local optimization. Spending 10 million baht to make the oven faster would accomplish nothing, because the oven was already waiting on the true constraint. Identifying the actual systemic bottleneck is the only reliable way to prevent fatal capital expenditure mistakes. Once you locate the physical bottleneck, you must measure the temporal math governing the system. This top timer represents takt time. This is the precise, steady rhythm at which customer demand pulls product out of your facility. The bottom timer shows cycle time. This is the actual amount of time it takes your factory floor to physically complete one unit of product. The relationship between these two numbers is a rigid mathematical law. If your cycle time operates slower than your takt time, the factory will inevitably fail to meet market demand. When managers ignore this math, the human cost is severe. Standard operating procedures fracture, workers burn out from forced overtime, and the entire system degrades. Line balancing, the engineering practice of forcing your cycle time to perfectly match your takt time, is a non-negotiable requirement for operational survival. To monitor this balance, industrial engineers rely on OEE, or Overall Equipment Effectiveness. This dashboard shows how the bakery scored a failing 45% by measuring 3 specific variables. First, the performance variable was tanking because the expensive tunnel oven was constantly forced into microstops, idling while it waited for the slow proofing room. Second, the quality score dropped to 80%. Those erratic microstops caused inconsistent oven temperatures, burning the croissants and generating massive amounts of scrap. Finally, availability was decimated. The dough mixers were chronically breaking down due to a lack of routine maintenance, causing unplanned downtime across the line. The intervention began by modifying the proofing room's temperature curve, accelerating the yeast activation to immediately shatter the primary bottleneck. Next, they deployed a low-code computerized maintenance management system. This empowered line workers to log machine degradation instantly, scheduling repairs before the mixers actually snapped. By replacing subjective floor observations with hard digital sensors and the OEE formula, management shifted from reactive panic to a state of predictive control. Returning to the OEE dashboard, the results of these interventions are clear. Siam Master Bakery doubled its production capacity and pushed its efficiency to a world-class 80%, all with zero capital expenditure on a new oven. This maps to the first rule of the operations diagnosis checklist. You must mercilessly locate the true physical bottleneck before spending a single dollar. Second, track your OEE using direct machine PLC data, avoiding paper logs that can be manipulated. Third, use SMED techniques to drastically minimize setup times and eliminate the urge to overproduce. Fourth, clear physical motion waste from the floor to keep standard work fluid. And fifth, shift your culture entirely to preventive maintenance. But there is a vital caveat. The most advanced IoT sensors and maintenance software will collapse if the workers operating them lack systemic understanding or the morale to maintain the standard. Taiichi Ono, the father of the Toyota production system, understood the intersection of human perception and mechanical efficiency better than anyone. He warned that the worst kind of waste is the waste we cannot see. True optimization is not about forcing human beings to work harder. It is the rigorous engineering of a system where work flows flawlessly, uncovering hidden friction and turning it into pure profit.